And to tell us more, or should I say to tell you more about the speaker, he is a professor and founding director of the Wireless Communication and Localization Networks Laboratory at the University of Ferrara. He received the HDE Pushkas Tivada Medal, the IEEE Communication Society's Stephen O. Rice Medal in the field of communications theory, and the IEEE Communication Society's Fred W. Ellisick Prize. Now, he served as editor for IEEE journals as well as chaired international conferences, and he has been elected chair of the IEEE Communication Society's Radio Communications Technical Committee and is a co-founder and elected secretary of the IEEE Quantum Communications and Information Technology Emerging Technical Subcommittee. He's an elected fellow of the IEEE and of the IET and has been selected as an IEEE Distinguished Lecturer. Ladies and gentlemen, let's welcome Dr. Andrea Conti.
Thank you for the kind introduction. I hope you can hear me and see me well. It's a great pleasure to be here. So thank you also to the organizer for the kind invitation. It's a really pleasure to be part of this workshop. So yes, today I'm gonna talk about localization, and in particular localization of things. I hope at the end of this talk you will get excited about this area of research, and if you are a student would like to know more about it. I will show you how localization of things is so far treated in the 5G ecosystems and what we can expect for beyond 5G ecosystems. So there are a few keywords in the title already: localization of things, 5G and beyond 5G, and ecosystem. And I hope that I will be able to touch base upon this aspect during the talk. Yes, I'm located at the University of Ferrara, and what you see at the bottom of this slide is the profile of a middle-aged castle in the center of the city. So location awareness. So we all know that localization is becoming more and more important. We are now in the technological era where we use, since already 3 decades, satellite systems, starting from GPS in some part of the world, and now globally the Global Navigation Satellite Systems, GNSS, through a constellation of satellites that send signals and an evaluation of the time difference of arrival at your GNSS devices is possible to know with a certain level of precision where you are. And this was initially thought for the localization of people or people inside some vehicles. And we will see that nowadays this is not enough anymore in terms of performance or in terms of needs for the new location-based services. And in fact, since we are in the era of the Internet of Things, we want to move toward the localization of things, which is the process of locating, tracking, navigating any possible collaborative or non-collaborative nodes. Nodes can be people, nodes can be objects or vehicles. Collaborative and non-collaborative means that these nodes are willing to participate into the localization process. So they want to exchange messages, measurements, observations with the network to be localized. Someone call it also active localization. While there is also the other important aspects related to the non-collaborative nodes, where the nodes don't necessarily want to be localized. The network needs to know where they are. And so this we will see is inside the framework of device-free localization. And to reach the goal of localizing the things, we can use global networks like GNSS or cellular, dedicated network like wireless sensor networks. There are some technology that we will briefly touch upon. and also use the source of opportunity, which means signals that are already on air for other purposes, for example, for communication, and try to exploit them also for localization, even if they are not designed or they are not thought for this localization purpose. Location awareness is a key enabler for a myriad of new applications. Just to give you a few examples, in the Industry 4.0, where there are cyber physical systems that need to be controlled and maneuvered based on where the good which is manufacturer is, and most of the time you need to know the state of this object under manufacturing quite precisely, also in terms of precision. So we really talk about high accuracy precisions, sometimes even a few millimeter or centimeter. Or in Agriculture 4.0, where you don't need that level of accuracy maybe, but it's important to know where sensors that are on the field capture information about the temperature, acidity, or other chemical quantities that are in your terrain, so that one can go and optimize the resources to increase the efficiency of your agriculture. And this is the concept of Agriculture 4.0. But location awareness is also very important for drone delivery, for example, or for drones used for safety purposes, because to control the drone, we want to know where they are precisely. Definitely, localization is a key enabler for autonomy. We can think of autonomous vehicle. In fact, ETSI has a standardized different level of autonomous vehicles. And we are all used to drive cars that have radars in the front, in the back, just to know if there are obstacles at a certain distance. But if you think in the future that you want to coordinate different vehicles that want to move in the space, you really need to know with high accuracy, few tens of centimeters accuracy, where they are located in space, as well as AGV. AGV are automated guided vehicles in industries, in factories. So robots that move into automated factories, as well as for tracking, accounting, and monitoring flow of people, so that are moving in big spaces like airport or malls. Is important to extract these types of analytics based on also on the position. So where the people are, how many people, and how flows of people move. For different purposes, from advertising to safety into those environment, and also for digital humanities. I'm from Italy, so allow me to put a few images from Italy, and augmented reality and virtual reality for museum are already a reality. If we are already present, and if we want to increase the level of services to people that want to access virtually some information of these archaeological sites or museum, is important to know with a high level of precision where they are. As well as for any distributed inference or environmental monitor application, where you have heterogeneous sensors that collect informations and information that needs to be processed. And if we want to process such information, we also need to know, depending on application with certain level of precision, where the information is coming from. So these heterogeneous sensors that are moving in the space need to be localized so that the information that they send become meaningful, and many others. So just to give you a few preliminaries about 5G and beyond 5G localization, localization is so important that the 3GPP, who is providing the technical specifications and technical reports for cellular system, define 7 levels of service requirement, which you can see in this table. You see in the first column 1 to 7, and these requirements are given in terms of absolute or relative position, in terms of accuracy, horizontally and vertically, looking also into the 3D network. And we can see that in some cases, the accuracy is sub-meter, from the service level 3 to the 7, we have meter or sub-meter accuracy requirement. Importantly, as well, with the same importance of the accuracy is also the availability, because that level of performance is required to happen 99 or more % of the cases. So your system, your localization system, really needs to be reliable. There is also some requirement on the latency that for some level, for some applications is in the order of the second, but in some of them is in the order of tens of milliseconds. So this is where really 5G is needed: latency, accuracy, availability. And you can see the last 3 columns that the different scenarios in which these requirements, service level requirements, are defined. And you can see that the challenges one are also defined for objects or vehicles or people that move rapidly in the space, even on a train, and need to be localized with that level of precision. So current system fail to provide that, or they can provide that in a very limited space where you can build an ad hoc system to reach that level of accuracy. They are challenging. And so what is really foreseen is that there will be an integration of native 5G measurements, the so-called radio access technology dependent measurement, RAT dependent, with radio access technology independent measurement, RAT independent, which are obtained through other technology. That's why we talk about 5G ecosystem. It's an ecosystem of technologies, an ecosystem of information, is an ecosystem of verticals and applications. And in fact, if you look into how the generation of the cellular network progresses over time, we can see that we move from the 2nd generation toward the 5th generation. We are now into the release 17, and discussion are starting by 3GPP, and discussion are starting for release 18, which is what will be called 5G advanced. And you can see that there are RAT dependent and RAT independent technologies, and that the more we move to our newer generation, the more the challenging, the more relevant will be and challenging will be the requirements, and so the more integration is needed. Location awareness is a win-win situation, because if from one side we can use all the net resources available in the network, or now we should say in the ecosystem, for improved location-based services, which is using the 5G RAT dependent. The 5G new radio measurements could be, for example, time difference of arrival measured from the position of a signal, or could be the angle of arrival. If you have a MIMO or a massive MIMO system, you just hear a beautiful talk about this. Or it can be, or one can also use resources or measurement from which are RAT independent, like using satellite, GNSS, or Wi-Fi that are in the environment, or Bluetooth, or ultra-wideband. Now, ultra-wideband is becoming more and more relevant, especially for localization, because it's for its capability to solve multipath, and so provide precise time accuracy, or also inertial measurement like accelerometer and barometer. Okay, so with this measurement offered by the ecosystem, we can have better accuracy in the knowledge of the position of the devices, and this enable new types of location-based services. But on the other end, that's why I'm talking about a win-win situation. On the other end, if we have better knowledge of the position of the nodes, then we can also improve smartly the management of the network. For example, if we know precisely where the nodes are, our beams, if we do beamforming in a MIMO or massive MIMO setting, can be more directed, can be more pensive toward the direction of the receiver or the transmitter, for example. And this, of course, improve the efficiency of the network, as well as reduce the electromagnetic pollutions in areas where this is not needed. At the network level, for resource allocation, we can allocate better the resources of the network if we know where our nodes are. For some applications where also latency is involved and we need to decide how to slice our network, which will be possible in a standalone 5G network, then the knowledge of the position also will play, of the nodes will play a role, as well as for controlling and maneuvering what we foresee would be the base station of the future, which will be mounted also on UAV to dynamically allocate the resources in space where needed. So win-win situation. So location awareness is relevant not only for the services, but also for the network management. So the network for the localization for the network. And the cycle of location-aware networks that we are interested in is depicted in this figure. Sometimes you will see at the bottom of the slide some reference from which the concept is described, or from which the figure is taken. And we first are interested into the theoretical foundation, what is the best that we can do in a certain environment with a certain technology, and then based on that, we have this sort of cycles which include the technology, all the type of measurements, which can be internode if they are radio measurements or optical measurements, or can be intranode, and if we are using some inertial device, plus some information about the environment, how the object move, or if we have a digital map of the environment. And then we have algorithms. Algorithms take all this information and need to do their best to provide you with the best possible accuracy, the position of the nodes. And this will see is an application of statistical inference, which include also, if available, the exploitation of mobility and perceptual models, and the cooperation in space and time, including the fusion of heterogeneous data. And then we have the applications that can be, I already mentioned application, we can add social networking, logistics, safe rescue, navigation in general. So we can classify our networks in different ways, anchor based on anchor free, if we have nodes in node position in the network, which will be called anchors because they are used as a reference node in these cases, or in terms of measurement. So we can have measurements of receive power or time of flight of a signal, which tell us from which we can estimate the distance between every pair of nodes, or we can have measurements that can provide us with the angle of departure or angle of arrival of a signal, so angle-based localization, or we can have measurement that allows if the object is in proximity of an anchor. For example, if you use Bluetooth, you mainly know that you are within a certain distance from your anchor. Classification can also be done in terms of technology. So in addition to the cellular network that we will mainly talk about and GNSS that I already mentioned, there are also some local technology that can be used. And if we want the best trade-off between accuracy and coverage, we really need to exploit, as you can see in the bottom left corner of the figure in the bottom, you can see that we need to really exploit the integration of 5G with ultra-wideband and wireless LAN and radio in some cases, because none of this technology alone provide the required service level. So it is an ecosystem because it's needed of integration of heterogeneous technologies for seamless localization. Ultra-wideband is playing an important role wherever it is needed some meter accuracy. In fact, the main manufacturers are now implementing ultra-wideband chips for precise time of flight estimation in the devices. And 3GPP, as I was mentioning, has envisioned the integration of radio access technology dependent and radio access technology independent measurements for achieving the goal of localization. And localization is a statistical inference problem where we start from a space of observation that provides us with measurements. Some prior information can be about the mobility model, for example, or the dynamics of the object, if it is a prior knowledge, or can be the digital map of the environment in which we are moving. And the algorithm needs to provide us with location estimate. And on the right side of this slide, you see a pictorial view of the localization process, where we start from technologies that offer us measurements, receive signal strength indicators, time of arrival, time difference of arrival, angle of arrival. These measurements are affected by uncertainty, of course, and algorithms need to do the best to take the positional information inherent in this measurement and offer to the position-based application the best possible location estimates, and has to be robust with respect to the inaccuracy. They might exploit memory if there is a temporal cooperation, and might exploit spatial cooperation with other nodes. For example, the concept of spatial cooperation is becoming very important in release 18 of the GPP, where manufacturers are talking about side link and the real exploitation of side link. Side link is there already since many years, but none of the operators want to really use it. Now there is some movement because the benefit of the cooperation among nodes is becoming more and more clear. Okay, talking about data fusion. So we want to fuse heterogeneous measurements, and I will be talking about a probabilistic approach, which is called soft information approach, and we will see how inherently such an approach will be able to learn from the environment, the conditions that are present. For example, line of sight or line of sight condition that really affect severely the performance of the localization, and can exploit a different type of measurements in time, angle, or inertial measurement, as well as different contextual information. Before we talk about this probabilistic approach, I would like to mention that the localization can be active or passive. So when the nodes collaborate with the localization process, we have exchange of measurement with our node. For example, from our base station, our GNB, to our user equipment, and vice versa. But there are also situations in which nodes do not collaborate or are not equipped with devices, but still it's important for the network to know if there are moving objects in the environment, for example. In such a case, we talk about device-free localization. We also talk about passive localization from the point of view of the source, if rather than using dedicated signal for localization, one exploit signals that are already on air for other purposes, for example, communication. And in such a case, we talk about the signals of opportunity. Okay. And we are in a framework for device-free localization, and we are in the framework of sensor radar networks, where we have node that transmits, node that receive, and the position of such nodes is based on information extracted from the waveform that these nodes reflect. So we need to be able to extract information on the position of the target in the sensor radar network setting. The object that we want to localize are called target, and we need to be able to localize this target based on information that we extract from reflections of the waveform. So this is challenging because any object reflects electromagnetic waves. Any furniture, any door, any person which is in the environment reflect. And so we will need to be able to remove these impairments, which is called clutter, associate components of the received reflected signal to each target, and based on these associated components, look into micro variation of this component and understand, try to estimate where the position of the target is. So the localization in the 5G ecosystem, I hope I was able to clarify already that is pretty broad in a sense, active, passive, with using different type of measurements, is an ecosystem that integrate and fuse different type of data. And to satisfy the challenging service level requirement, classical methods typically fail. And what are classical methods? Classical methods are what the so-called single value estimate methods, where based on the measurement of time, or based on a measurement of angle of departure of arrival, or based on an estimate of the power, measurement of the received power, one determine what is the distance between a pair of nodes, typically an anchor and the agent or the target, and then using also some prior information if available, the localization algorithm provide us the coordinates of for the positional state of the node. This is an approach which is similar to hard decoding, if some of you is familiar with coding theory, where you, rather than using all your sample, you make a decision on what was the received symbols and bits, and then you decode. And of course, this choice requires some quantization early in the process, and quantization is always loss of information. So this is not this classical approach. This is why classical approach fails. In addition to the fact that they are not able to take into account often the condition, the propagation condition in the environment, for example, line of sight or non line of sight, that severely affect, in addition to multipath, the estimation of the time or the angle of arrival. So recently it was proposed a new approach, which is a probabilistic approach, which is based on soft information. So rather than making a decision of what is the distance, what is the angle, every time we receive a measurement, we built a probabilistic description on what the distance could be, what the angle could be. And this has some significant benefit, because it's more robust to detrimental effects like multipath line of sight or line of sight conditions. It also allows for easy integration, because this can be done independently of what the measurements are. And it can also is a system. We will see that is a system that will learn the condition of the environment, and that's why it can better exploit the measurements. So some insight. Basically, we are saying that rather than making an hard decision on the time angle based on each measurement, what we are saying is that we keep some probabilistic description of what the time or angle could be. And this is represented by these LY1, LY2, LYN that you see in the right of the figure that I'm showing you now. And those are generative models. Those are functions that describe probabilistically how the measurement is associated with the time, angle, or other features that are related to the positions, okay, probabilistically. So we're talking about estimation of PDFs. And to do that, and of course, the environment are so cumbersome that we cannot assume any analytical model or easy model like Gaussian PDFs pretend that it works in a particular environment, because this is why classical algorithm fail. Rather than that, we need to learn from the environment. So this is where machine learning also come into play. And I will give you some more detail when I will talk about this concept of soft information applied to 5G. And just to give you a pictorial view of what data fusion means and what probabilistic description of the distance or the angle or the context information means, you can see in the right figure now a scenario with the purple contextual information. We know that the two anchors, the red single and the agent, the blue circle, are in a certain environment with that S shape. And for example, from the anchor in the bottom left, we are able to measure times and so distances, and we have a description, a soft range information that describes probabilistically what the distance could be. From the top right anchor, we have a measurement of angle, for example, and so we can see probabilistically what the angle could be. And then the purple is the context. We know that our node is inside that environment. The context could also be a dynamic model, for example. And then, by fusing, multiplying these informations, we obtain in the bottom of this right figure the new soft information, and maximizing the soft information that we see would be basically likelihood in a non-Bayesian setting. We will be able to determine more accurately where the position of the node is. So the workflow is that in an offline stage, we exchange measurements. Measurements are this vector Y. The received signal contain positional information through some features, data, which is, for example, time or angle or any other type of features. The information, the measurement that we take are typically rich. So in some cases, dimensionality reduction, for example, to some principal component analysis method might be needed. And then there is a mapping of the features into and then measurements, which is this F hat, which is an approximation learned from the environment through, for example, supervised machine learning techniques of the relation between the measurement in the reduced space and the features. And then in the online space, every time a new measurement comes, in the online stage, every time a new measurement comes, Y new, it is mapped into the reduced dimensionality space, and we consider the generative model for that specific measurement as our likelihood. So in the 5G setting, just to give you one example, for example, using the positioning reference signal, the PRS, for downlink time difference of arrival. The PRS is defined as an IFDM signal dedicated to localization. You can see in the top left the frequency time mapping of this PRS signal, an example of it. And based on this PRS, it's possible to estimate the time of flight of a signal between any base station and the user equipment. And the 5G localization works in a way that is based on time difference of arrival. So the one base station is assumed as a reference base stations, and all the times of arrival are, we take the difference of all the time of arrival with respect to the time of arrival of that specific base stations. Of course, here there is a key important problem of how to select the best base stations, and that works on it. And in such a case, the soft information-based localization approach associate this time difference for a given time difference of arrival, provide the likelihood in a Bayesian setting as a function of all the possible distances between the object in an unknown position P and that base stations. And by multiplying, because these likelihood have uncertainties which are independent, the measurement can also be taken with different technologies from one anchor to another anchor. By multiplying these, it's possible to then apply algorithm like that maximize the likelihood or that maximize the posterior probability, or that minimize the mean square error. Any type of algorithm can be used. What we see on the bottom right is a representation of two hyperbolas in probabilistic sense. So you see a shape which is not just one hyperbola, as in the figure above for single value estimate, which represent two time difference of arrival when anchor 1 is taken as a reference, and one hyperbola shape is related to the GNB2, next generation base station 2, or GNB3. These also allow to easily perform data fusion, because this is like you can have any shape based on any type of measurement that we take. For example, we see here an example of a time difference of arrival from 5G on the left with a time of arrival from Wi-Fi, and you see the fusion of the two lines. And you want to find the maximum in that blue area on the right. Okay, of course, there is a problem of how to approximate the generative model, so the shaping of your likelihood to probabilistically account for any possible value of the features, of the positional feature associated to a measurements, and there are work we've been developing some work. You will see some reference later for how to efficiently do these offline phase and this online phase. Okay, so I think I would like to move a little bit quicker, so I will skip a few slides. I just want to give you an idea on the benefit of the soft information based localization when applied to an ultra-wideband network. For ultra-wideband network, according to the 802.15.4a channel models, indoor residential, the bottom left figure, outdoor, the bottom right figure, you see the localization error outage, which is the complementary cumulative distributed function of the abscissa. The abscissa is the error in the localization, is the absolute value of the difference between the position estimate and the true position. And you see that the more you go to the left, the better it is. And you see that with the same measurement, single value estimate provided the green curve. We have 3 green curves according to the different no line of sight probability. Toward we move with soft information toward the red curves, which are much better. So, for example, with only 10% of outage, meaning that the availability of the system with a certain performance will be 90%. In red, we can have a couple of meters, whereas with a single value estimate, we will get 6-7 meters of error. So, to analyze the performance in 5G and beyond 5G network within some international project, we've been developing some simulator that is able to generate precisely all the aspects contained into the technical specifications, from the signals, PRS, SRS, multi-RTT, to the parameters of the antennas, the polarization, the noise figures, to the scenarios where the GNBs are according to the 3GPP technical specification. We use the quadriga channel simulator. We implemented waveform processing, and we will be able to show the difference between 5G localization or beyond 5G localization with the classical approaches with respect to soft information approaches. These are some numbers related to the parameters contained in the technical specification. But just to give you a few examples, we are in scenarios for urban micro, the left, and indoor open office, the right, standardized by 3GPP, where you have in a certain environment a certain number of base stations. And this certain number of base stations and this different environment, outdoor versus indoor, provide you different probabilities of having at least 3 base stations in line of sight or no line of sight, remember, line of sight or non line of sight conditions significantly affect the localization performance, and based on that, and based the soft information has shown that is capable of learning this situation and provide better accuracy. In fact, in the urban micro scenarios, you can see, for example, that while in the technical specification, your empirical cumulative distribution function of the horizontal localization error is given by this symbol, asterisk and the crosses, at 50, 60, 70, and 75 and 90 percentile, which provide when the 90 percentile error in the order of 8 meters for urban micro scenario. You can see that with soft information, you can improve significantly performance, and with the same measurement obtain a couple of meters of error at 90%. And we show type 1, type 2 for different configuration of the positioning referring signal. And similarly, you can see the gain. You basically see how much you move from your symbols to the curves, to the lines toward the left. And you see that there is a significant improvement of the performance by using a probabilistic approach rather than single value estimate. We also showed the performance in after this work, which is the review. We also showed the performance of localization in by exploiting a millimeter wave, so FR2 instead of FR1, and we can see that the performance using millimeter wave in the 3GPP 30 giga standardized scenario is really much improved. There you can also use the angle of arrival and in addition to time of arrival, and you improve the performance and you have sub-meter accuracy. So this shows that it is possible to reach the service requirement asked by 3GPP. And then we were also able to show the improvement of the localization when using or fusing also data from Wi-Fi. And you can see that from single technology, the dash is Wi-Fi only or 5G only, using classical approaches. With probabilistic approach, soft information, you improve and you have the blue and the red, and you improve even forward the green curve when you go to with the data fusion. Okay, so in summary, soft information approach seamlessly fuse different type of position related measurements, easily integrate, can be easily integrated in 5G architecture and adapted for future beyond 5G networks, and it can exploit different type of measurement defined in 3GPP settings. Okay, so I will. I think my time is now over. I would like just to conclude with a couple of slides to tell you where we are going. In particular, I would like to tell you that if you are interested in localization, the ComSoc has put together a best reading series on network localization and navigation, and this is the link for it. And I hope that you might get interested into this best reading, and feel free to contact me if you have any questions. But what is next? Because I mainly talk about 5G localization, and for some of the aspects like the real exploitation of millimeter waves, we were already in sort of beyond 5G, or let's say 5G advanced, at least 18. But what is next? So what is beyond the 5G ecosystem? So definitely there will be integrated sensing and communication, meaning that we want either to integrate the sensor radar network and the 5G localization together. And this can be done in two ways, as separate networks that fuse the information at a higher level, or by doing the two things really together. So using signaling that can serve for both localization and radar, radar and communication, or localization and communication. So there is the problem of how to jointly optimize the resources. Another aspect is understanding how the multidimensional stochastic sampling is affected by uncertainty on the position of the nodes, and the use of intelligent surfaces to being able to control the reflection of the electromagnetic waves so that we can improve also the localization in scenarios that are affected by abstractors. And in the near future, after 6G, probably quantum sensing, so exploiting quantum mechanical properties to do a better illumination and a better sensing and a better estimation of distances and position also. So as a takeaway message, space is the next frontier. This is a quote from Star Trek movie, but this was before that a quote by the pioneer of digital synchronization, Dr. Bill Leasy, and at the USC, and basically all the works on MIMO, wireless MIMO, account for it. But if the space is the near and is the next frontier, we really need to know where we are in the space. So location, location, location. And with that, I'll conclude my sharing, and I will be happy to take any question, if any, and I invite you to contact me for further discussion. Thank you.
Thank you so much, Dr. Conti, for that insightful presentation on localization of things. And of course, now we'll move on to the question and answer segment. We have a few questions from the audience right now, starting with this one. Can you tell us more about 3GPP scenarios and localization in them? Dr. Conti, your thoughts?
Yes. So the scenarios are challenging. The requirements are challenging, as I was mentioning. And in fact, for a matter of time, I skip a short video that shows something that I would like to maybe I can take a couple of minutes to answer this question and show this also by exploiting this video. I think this could be interesting for someone. This is just a guide representation of the work that we've been done on probabilistic approach for localization, and this guy this graphical user interface show is an interface for the core of the method that I propose, but might give a clearer vision of what is the difference of using classical approaches with respect to probabilistic approaches. So if you are fine with that, I can show a 2.5 video for answering this question. Can I go?
Sure. Let me just check. There's a 2.5 minute video from Dr. Conti. Can we play that? Are we able to let him play that?
Let's try.
That's
If you can show me that, okay, thank you very much. So I hope you can hear the audio. I will add a few words in case. So you see on the top left the 3GPP scenario that you can select. On the top right, you see all the characteristics that you can select on the signals. In the top, in the bottom left, you see the soft information and how evolving times, and on the right, the performance. You will see red trajectories estimated in real time, as well as red performances from 3GPP like classical methods, and in blue, the soft information one. So, okay, you see here your green agent, which is moving. You see the red crosses, which are the classical approaches, and the blue crosses are the soft information. So you see that in this case, we are using angle of arrival, and you see what is the improvement of the blue with respect to the red. Now you can see that the shape of the soft information is changed because we go from angle of arrival to time difference of arrival. So now you have hyperbolas type of probabilistic descriptions, and you see what the performance are. These are performance at millimeter wave at 30 gigahertz by fusing angle of departure in this moment and a downlink time difference of arrival. And different type of measurement in the standards can be used.
Thank you so much, Dr. Conti, for that very visual elaboration to help
Okay,
our audiences
so
better
this
understand.
was. I don't know if the audio was possible if I shared the audio. So I prefer to talk. I hope I didn't talk on top of it. But yeah, this is just to show what happened when you use one approach or the other, and the fact that you move from sub-meter accuracy to sub-meter accuracy.
Thank you so much. And we've got a few more questions for you, Dr. Conti, from our audience. The next question is,
Yes, please.
can 5G, 6G, or 6G localization cover both indoor and outdoor accurately and replace GNSS and GPS?
This is a very important and relevant question. So thank you. Well, this is the goal. This is the hope. We have seen that the service level requirement defined by 3GPP are much better than what you can expect to do with the GNSS, especially because there are environments that are in which GNSS is challenged. But as I try to say, there is no one technology that surpasses the other. It is really an integration of technology. By exploiting data fusion and all these technology, we hope that we can achieve this sub-meter level accuracy in 99% of the cases that the GPP asks for. It's difficult. It's not going to happen in 5G like this, because there are first of all, the operators need really to unleash all the bandwidth for dedicated signals. Plus, there is the need to develop methodologies for extracting the best out of any type of measurement and fuse them. So the probabilistic approach based on soft information that I mentioned in my talk seems a good way to do this, and this is why I offered this in this talk.
Thank you so much for a very insightful answer. We have another question that just came in, and this one is, can quantum effects be used for enhanced localization accuracy? Can they, Doctor?
Okay, so I'm so glad I received this question, even if I don't have a clear answer. Okay, so I'm working. I start working in my group on this. So I think I have a limited view on things, and I like to give kind of crystal ball answer. But I think they will. You shouldn't expect this in the next decade. So towards 6G, I think it requires more time, because we don't have at the moment devices. The world of quantum is mainly related to quantum computing. So far, we are working for quantum sensing and quantum communication. But there is this concept of quantum illumination, where you emit quantum states, and based on the states, on the discrimination that you can do with the receiver, you are able to understand better, for example, some what happened or which type of quantum channel you have seen, and these include also better estimate, for example, of the distances. So I think that in the future, this is what we are working for. This is where research is starting now, and I hope that many of you will be also interested in the quantum communication and sensing, because it's really something that for your future, in more than 10 years from now, will become relevant. So I think my answer is, I think yes, and this is what I am personally also working for. If this is going to be really effective on a large scale, like instead the localization with GNSS or smartphone, I think it's going to happen in some decades. It's not going to be tomorrow, but I think that's a very important and interesting direction.
Thank you so much, Dr. Conti, for addressing that question. We have our next question that just came in, and this is, do you have any comments on the localization with soft information using factor graph for 5G and 6G? What are your comments on this?
Okay, so Another important point. In fact, there are already algorithms, classical algorithms, that are based on the concept of network factor graphs. Okay, so when you describe your network with a factor graph, but you have the different nodes, and so the point is that these nodes needs to exchange messages. So to exchange these messages can be a representation of the generative model that I was mentioning. Okay, so in fact, the probabilistic approach that I was showing is already kind of related into this question, and already look into the implementation with network photograph. Network photograph is there is some interesting work that dates back in Proceeding of IEEE 2009, and more recently in the Proceeding of IEEE 2019, where the soft information approach was proposed. We have shown also how to implement a distributed localization via soft information, and to do this distributed localization, you can see your network of nodes as a network factor graph that were on each link of the graph you exchange messages which are associated to this likelihood. So definitely yes, they are related, and they can be implemented in this way, as long as you allow side link. So for the implementation to the 5G and beyond 5G, we need the operator to open up the side links, so the direct link among nodes. And it seems that they are convinced about the importance of it. And in fact, in the first meetings of the 3GPP for the release 18, this is one of the 3 key points that is mentioned, in addition to how to use artificial intelligence and machine learning for localization.
Thank you so much, Dr. Conti, for those inputs on that last question. Still have a couple more, and hopefully we can finish all of them. The next question is, can the localization approach you mentioned be directly implemented into 5G architecture? Can it?
Well, in fact, yes. So we are developing these things inside some international project. I can give you a direct example of it, because we are exactly working on this. So there is one European project which is called Locus, where we are implementing atomic virtual function and atomic services that are implemented at the architecture level. So we have access to the cloud of an operator and the virtualization of its network, and this algorithm we are implementing into the network, and we are showing how they work inside that project. So yes, it doesn't require any change into the measurement or functions that are already defined in 3GPP, and this is important because we can do application-driven research, but that can be hopefully impactful only if industries and manufacturers and operators then are able to take into account, and to achieve that you need to be compatible with the 5G architecture, and in such a case it is.
Wonderful. I think we can squeeze in one last question just before we hit 4 p.m. Over here in Singapore, and this is this one. Can you elaborate on multi-target tracking with device-free localization?
Yes, and to do this quickly, can you show my slide again, if possible? Okay, thank you. So the point is that you see that you need to be based on the reflected signal. So you have your target moving in the environment, and you have, for example, a transmitter that emit a signal, and the waveforms are reflected by the target and reach some receivers. And this receiver see waveforms that are varying in time, and based on these received waveform, then one can estimate the position of the target. And in fact, one can also estimate the position of multiple targets. So for example, here you see a video of a single millimeter wave MIMO radar, And in this video, you see 1, 2, 3 persons that enter the environment, and they are tracked applying the method that I mentioned you before into this sensor radar network tracking. So this is just a real-time experimentation. You see the video of the people moving on top, and you see the information which is extracted below. So I hope that this video show a little bit of what you can do with for device-free localization. The challenges are that you need to understand which component of the reflected signal is associated to each target, and you also need to understand how to develop methods to remove the reflection for things that are not related to the targets.
Thank you so much. Thank you so much, Dr. Conti, for helping to answer all those questions from our audience, and of course for that intricate discussion on localization of things. Thank you very much.
Thank you. It was a pleasure to be with you all.